so in my group we study complex social systems, and we focus on flocks of birds, schools of fish and groups of primates. Yes, at this conference we presented 2 papers related to predator-prey interactions with birds. And first my PhD student, Robin Mills, he presented the advantages of peregrine falcons when they execute an attack strategy which is called the stoop. And in case of the stoop, you see that the peregrine falcon goes more or less vertically downwards and attacks this way its prey bird. And he showed that the stoop is mainly advantageous in case that the prey is moving erratically, unpredictably. He did this in a computational model. And myself, I presented work which we did with 2 other co-authors, a master student, Lars van Zijdam, and our scientific programmer, Hanno Hildebrand. And what we studied here is what you see in flocks of starlings. You know, you have these beautiful flocks of starlings that coordinate through the air with, let's say, 20,000 individuals. And if you see them, for instance, above Rome, when the flocks are very, very large, you have moments whereby they are attacked by a peregrine falcon. And in these moments you see these huge flocks, often they are vertically, and you see that in these huge flocks a black band moves downwards. And you see that it's triggered by the peregrine falcon, so the peregrine falcon attacks, and then you see a black band moving downwards. But these huge flocks are very, very far away, a kilometer away, and our telescopes and cameras are not good enough so that you can see what do the birds do in case they build these black bands moving downwards. So we thought we studied this in a computational model. We take a computational model and we try out several escape maneuvers of the birds, and then we see when do we humans observe these black bands moving downwards. And these black bands moving downwards are called agitation waves. But for this you first have to build a computational model in which you have flocking behavior when there's no attack by a peregrine falcon that resembles empirical data of real flocks of starlings. And this we built, we have a number of rules in it. On the one hand, these birds coordinate with each other in the sense that they are attracted to others, so stay together, they align with others, move in the same direction, and they avoid collision by turning away. And they do this coordination behavior with only their 7 closest neighbors, because in empirical data it was shown that only the 7 closest neighbors are non-randomly distributed, whereas the others are kind of randomly distributed, so probably they adjust their coordination, their movements to their 7 closest neighbors. And then we added to this that they fly. And this is unique in our computational model. We have the only computational model in which there's flocking and flying. And flying we added in a simple way, in the sense that the birds do not have flapping wings, but they fly like an airplane, fixed wing aerodynamics. And then we made them stay more or less above the sleeping site, the site for sleeping. And this resembles very much empirical data in the flock properties, the size, the density, etc. So it was good enough to study how do you get these agitation waves, these dark bands. And agitation waves you see in many animal species, also in fish schools. You see a band moving away, and often it's a dark band, and for herring it has been argued that it's a density band, in the sense that the fish move fast away from the predator, closer to others, so you had compression, and this compressed band moves away. But there are also cases where you see a silvery band moving away from the predator, and this happens in anchovies. And anchovies have a silvery belly, and they have a dark background, so they must have been rolling. So you see that they roll, they make a kind of skitter movement. And the same you see in dunlin flocks. You see that the color of the flock is, let's say, grayish, and suddenly turns brown and then turns white. And that is because suddenly you see the belly, kind of they turn like this white, or you see the back, which is dark, and so you see this color shift. and this goes in a wave. So we were thinking in starlings, it could be that they speed up away from the predator, so they move inwards, you would get a density wave. Or you could imagine, like you see here in this figure, that at one moment you see very little of the wing, at another moment you see the whole wing surface because they roll sideways, skitter sideways. So if they turn away, they have to roll over the side. And we tried out both maneuvers, and we made it such that if a predator attacks, the close-by birds are skittering or speeding into the flock, so escape maneuver, they show an escape maneuver, and then subsequently 2 to 7 closest neighbors show the same escape maneuver. And if you take as the escape maneuver moving fast inside the flock, we don't see anything happening, although we know that it's transferred through the flock by copying by the closest neighbors, 7 closest neighbors maximally. You don't see anything, you don't see. But, so apparently it's not the density wave, but if you see in the computational model that they roll over their shoulder, make it a skitter movement whereby they roll, and suddenly you see a larger area of the surface of the wing, then you see a dark band moving away, like you see here. And this has no density aspects, because if you make the birds into balls, and you give them the same escape maneuver, you don't see anything happening. So that is then subsequently a hypothesis for empirical data, study in empirical data whether indeed, if you can get the flocks closer, this happens by means of rolling over their side. And so we studied in the model also what causes the speed of the wave, because many people have been thinking the speed of the wave is so fast, how can it be? And indeed, the speed empirically in waves of starling flocks is 13.5 meter per second, which is faster than the bird flies themselves, faster than the predator flies at cruise speed. But if you think of it in terms of that they have to copy the behavior of their closest neighbor and they have a certain reaction time, you can understand it. Because the average distance to the closest neighbor is 1 meter, the reaction time is 76 milliseconds. So the speed should be about 13 meters per second, which is exactly what they do in reality. So we could easily match for the empirical data the speed in the computational model of what we see empirically. So these are predictions for empirical data. You could now study what happens in denser flocks. We expect then that the speed of the wave is slower, and so on.